So welcome to the coffee lecture on rapid prediction of physical and ADME properties with ACD Percepta software. Welcome to everyone here in the room and welcome everyone in Zoom. I'm Joži Sadolens. I work for the Chemistry, Biology, Pharmacy Information Center, and this is now the last coffee lecture in the summer series. It's going to be a bit more specific today, more chemistry oriented, and I hope you will enjoy it. So I would like to tell you first what ACD Percepta is. ACD Percepta is a software which is developed by ACD Labs. For those who don't know ACD Labs, it's a big company. Also SciFinder, for example, has predicted properties and spectra from ACD Labs inside. So it's kind of an industry standard software for prediction of physical, chemical, toxicological, and ADME properties from molecular structure. Now, what is important to know here is that predictions are done based on empirical models. So there's no quantum chemistry or simulations behind. And there are large training libraries involved, some of which you will see, and advanced algorithms which are quite well described in the documentation. In InfoCentrum, we license this software and we license it as a single seat software. So there's only one person can work with it at once. If you're interested, let me know and I'm going to tell you how to access it. And here on that slide, I'm listing some modules that are available with us. And for example, we can predict octanol water partitioning coefficients, pKa constant under standard conditions, basic physical properties such as boiling points, solubilities, and then ADME properties such as BBB permeation, cytochrome P450 inhibitors, PGPC specificity, and even more, as you will see in a moment. From here on, I would like to make a live demo. And to make a live demo, I need to log into our virtual machine. So it will take a minute. Thank you. So here we are. This is our Windows server, and on that desktop we have an ACD Labs folder in which you can find ACD Percepta. And now I hope you can all see the screen very well. ACD Percepta software has in principle 3 panels. In the first panel, you have your projects. You can see the substituents that are used for predictions that are based on substituents and incremental predictions. Then there are libraries which you can train also yourself, and libraries and databases which are used to make empirical predictions that you will see in a moment. I would maybe just for demonstration like to show you LogP library that is here. LogP database contains over 18,000 molecules, so it's an interesting database on its own already. And if you look into that, you have here the LogP values for different compounds. First, there are very simple ones, and then they are more and more complicated. There's always a value given and a reference where the number comes from. If you will then, of course, want to calculate LogP for one of those compounds, then this database will be used. Similar ones we have for pKa, for solubilities, and so on and so forth. So this is all available through the software. That's the first panel, which we in principle will now use just to create a project. Then the second panel, which is even more important, is the prediction modules, which I was just mentioning before. So if I click on this little plus here, you see here different prediction modules. So BBB, permeation, LogP, and so on. So I would like to show you a little bit of this, how this works. I'm going to create a new project now to calculate blood-brain barrier permeation. And now if I click on that, of course, I need a structure somehow first because it's all structure-based. I can either draw it, I can search for it with InChI, key, smiles, or I will just take it from a library now to be faster. I'm going to take as an example nortriptyline. Which is a drug that is used for treating depression. And the reason why I chose this drug is because I wanted to show you a little bit of an activity on the central nervous system. And what you can see here, we have here a structure, and then here you see the main physical chemical components that are used in the prediction. That is LogP, pKa, and fractional unbound plasma. You can go and change those values, and then of course the prediction will change. But these are the values that are taken from the prediction models that are in the background of ACD. All right, so this is the input, so to say, and that's then what is calculated: the rate of brain penetration, extent of brain penetration, and brain plasma equilibration rate. Now, if the light is green there, it means it penetrates. So it's a drug that goes into our nervous system and does some activity there. What you can see here also that is that this is not a passive transport, but it's predicted as carrier mediated transport because yeah, this is an organic cation, which can so it can be protonated here. And then at the end you have a scatter chart where you have a log PB versus, so basically this value versus log PS. And in that part, in the blue part, you have CNS active compounds, and here there are CNS inactive compounds. The green square is our compound. And you can see it's under the CNS active part. So this was one example of prediction that can be done using this software. Now I would like to move to maybe something a little bit more physical, partitioning coefficient. So let me keep the same molecule and go to look into prediction of partitioning coefficients for this molecule. As you can see here, there are two algorithms that are available, the classic and the Galas algorithm. The classical algorithm is very simple. It looks at the functional groups of the molecule and incrementally calculates a value that is then given up here. The Galas algorithm looks at similar molecules that are in the database and also suggests a value for the partitioning coefficient water octanol. What you can see here, it's always worth to look under similar structures. And if you do that, you'll see now nortriptyline was exactly actually one of the molecules that is in the database that are used for training. So we have here a lot of literature on that molecule with measured values, yeah, not just predicted ones, which is nice, yeah. This happens sometimes, but not always. And if not, then you have to look at the similarities. So log P now predicted, so the Galas algorithm predicted log P of 4.41, which is slightly lower than the classics algorithm, but it's not exactly the same at what has been measured. That is now very interesting. So the consensus log P, which is at the end given, is the weighted average of those two results, and it's 4.76. So that is another example of a prediction. What you can see here, I think, from this example, this one always have to be a bit careful and look at the references, look at similar structures. And if there's a big deviation, one should think why it is there. Yeah, so that is something to keep in mind. Then maybe cytochrome inhibitors. You can also look at that if a compound is a cytochrome P450 inhibitor. And what the program does here in this case is it looks at 5 isoforms of P450 and checks the inhibition probability of that compound against those isoforms with 2 different models, one where IC50 is less than 50 micromolar and one where, so this is more of a general model and a bit more of strong model where IC50 is smaller than 10 micromolar. And then you see here, if it's red, it shows you that the chance that this molecule will inhibit the isoform, the second isoform is actually quite big. So one has to look into that, and the error bars is also not so big. The green means that actually it will for sure not inhibit. The gray means that the value is undetermined. Yeah, so here we have a potential risk here and there. And then if you go to less IC50 values, then actually only the second isoform can be a problem. And this you then also see down here. You can go and check the different isoforms, and nortriptyline, which is an exact match from the database, what we've seen already before. It tells you for the second isoform that is certainly an inhibitor in the range of 50 micromolar or less. This is another example, and now the final example that I can show you is pKa prediction. That is what comes, this question we get more often in the Info Center, how to predict pKa. With this software, again, there are two algorithms. For pKa prediction, I will now search for a different molecule which has a bit more protonation states. And I'm going to take sterazine for that. Yeah, so here we have now lots of nitrogens, which can be protonated, deprotonated, and so on. And I'm going to go here and do the prediction via classic algorithm. Classic algorithm just simply looks at those states and says, what are the pKa values? I'm not going to go into details of calculation protocol here. It is rather simple. What I would like to show is the Galas algorithm, which I find very interesting, again, based on similarity. You get this plot down here where you can go through with a bar. On the x-axis, you have pH, and you can, for each pH, let's say pH 2, you get a result, which protonation states are available. You can see it here on the right-hand side. So at pH 2, we have protonation state 4. There's that one. For 45%, protonation state 2 and 3. So you see them. For 51%, and in the end, the protonation state 1 for 6%. So you can see what is protonated at which pH, which is, I think, very important to know. And then if you're at 7, we have mainly protonation state 5. Yeah, so that is what this prediction can give you. And here is then the plot where you can see how those protonation states go from one to another. With that, I actually have to stop showing you the predictors. I would just like to show you one more thing, and that's a spreadsheet option, which is very useful if you have a lot of structures and you would like to screen their properties. So you can go here under import and import, for example, SMILES, all of them in. You add them. So I think if I do that, it will just import them. And then you can go to, you can mark the column with structure, you can go to calculate, you choose the properties you would like to calculate, let's say boiling point, vapor pressure, enthalpy vaporization, flash point, just as an example. I add them to the properties I wish to have. Now there's a little plus, it means that you have, of course, to add pressure at which you want to calculate. This is in millimeters, so I put 760, and vapor pressure, temperature, let's say 25. I say, okay, cannot proceed because he didn't remember, obviously, what I typed in. 25, enter, okay. And then it populates a table. And basically all the properties that can be predicted using ACD Percepta can then be added as these columns, and then you can, you can analyze them, you can sort them, and most important, you can export all this in different formats, and then continue working with the data. There's more, but I have no more time to to demonstrate. So I go back to my slides, and maybe I just show you one more thing with the slides. So there's one more thing which is quite nice, and it's called Structure Designer, where you can load a structure, a marker fragment you would like to change, such that your library of analogs that you would generate then would have a specific property. So basically, if you have here a, let's say, an OH group, and you would like to have something else, and so you're open to variation, you can say what kind of log P or pKa you would like to have for your molecule. And then the program will recalculate based on all these predictions and suggest you analogs that would match the properties that you like to have. So this is a little bit of the intuition we chemists have, but here I think we get even more ideas on how to change molecules to satisfy certain conditions. Right, there's a lot more. And if you go into this program and click on this little question mark here up, you'll get to the documentation, and the documentation is very extensive. It explains how to use the modules, and it also explains how the algorithms are done. Coffee lecture card is available here, but I can also add then later in the chat the URL, so you can download it. And I would like to tell you that this is the last coffee lecture in this series, in this summer series, and we have this time recorded all of them, and we put them on our YouTube channel. So if you would like to listen to some of them which you have missed, or recommend some to your colleagues, please look at our YouTube channel. Thank you very much for your attention, and hope to see you in fall. Now, if you have questions, just unmute yourself or ask questions here in the room.